Alright, welcome back to Unit 9 on limits and derivatives. If this is working right, I'm using a headset, so you shouldn't hear the clicking of my pen as I go through this video. So hopefully it's working. This is video 6. We're looking at the average rate of change. You should have a note sheet, and this is the first example on that sheet. So the average rate of change is the total change divided by the time for that change to occur. So we're just looking at a rate of change that happens on a certain a plot of data. So here we've got the population in Schaumburg, and we're looking at a function of time. So time is our x value, and y is our f of t, the population. So in 1850, there was a population of 3,200. In 1860, a population of 4,700, and so on. So as we go through this, we're going to be using a slope formula. And it's important to remember that A is less than B. And that really occurs for our t values that we're always subtracting, for example, 1860 minus 1850. That doesn't mean the population must be going in a positive direction, but that our time is always going in a positive direction and increasing. So let's start with the first one. So our A value for this case is 1850. Oops, I'm going to write B there. So our A value is 1850, and our B value is 1880. So this is looking like f of 1880 minus f of 1850 over 1880 minus 1850. So let's go ahead and substitute those numbers in. So f of 1880 is 10,400, and f of 1850 is 3,200. All divided by 1880 minus 1850. So we have the change in the population divided by the change in time. So I'll go ahead and calculate that. And we get 7,200 divided by 30. So we can take a look at the rate of change to be 240 people per year over that period of time. Let's look at the next one. So from 1880 to 1900, so year 1900. Alright, so we're going to go ahead and take a look at those two values. So again, I have f of 1900 minus f of 1880 over 1900 minus 1880. So we get 27,800 minus 10,400 over, we're looking at 1900 minus 1880. And let's do the subtraction. So we get 17,400 divided by 20. So our average rate of change over those years, those 20 years, is 870 people per year. We should label that people per year. All right. Example 2. A barrel of maple syrup is tapped at time is greater than or equal to 0. So this is number of seconds, minutes, that our time is being measured in, and how much maple syrup is pouring out at any given time. Okay, so for 1 minute, or 0 minutes, we got 0 maple syrup. 2 minutes have passed, and we've got 36 gallons of maple syrup. 4 minutes, we've got 54 gallons of maple syrup. Compute the average rate of change of f of t from 0 to 4 seconds and from 4 to 12 seconds. So we're going to be looking at from 0 to 4, and then we're going to be looking at from 12 back to 4. So we've got f of 4 minus f of 0 divided by 4 minus 0. And that's for this first one. So that gives me 54 minus 0 over 4 minus 0, which is 54 divided by 4, or 13.5 gallons per minute. Let's look at the second one. F of 12 minus f of 4 divided by 12 minus 4. So f of 12 is 100 minus f of 4, which is 54, and 12 minus 4. So that gives us 46 divided by 8. So that gives us 5.75 gallons per minute. Now, why might it be going down? Well, if a barrel of maple syrup is being tapped, at some point, there's not that much maple syrup left in our barrel, so we could have a slower rate of maple syrup pouring out of this barrel, because there's less maple syrup in the barrel. Example 3. The amount A of T in milligrams of pain reliever in a patient's system after T minutes is given by A of T equals A times time, 8 times time, and E to the power of negative T divided by 50. So we're going to remember where to find this in our calculator. But again, we're doing the same thing. We're going to have A of T, that'd be A of 50 for this problem, A of 50 minus A of 0 divided by 50 minus 0. Now, for these, we're actually going to have to substitute that in to find 50. So I'm going to have 8 times 50 E to the negative 50 divided by 50. And I'm going to be careful when I enter that in my calculator. Minus 8 times 0 E to the negative 0 over 50. Well, already knowing that 8 times 0 is going to wipe this out, I should be okay. That I don't have to worry about calculating that one, because 0 will wipe out this entire quantity. So let's go ahead and calculate that. Very carefully in your calculator, enter that in. You're going to have 0 parentheses, 50, close your parentheses, E. And if you've gotten where E is located, you can find it in a couple places. You can find it above your ln, which is next to the 4, or you can find it above your division sign using the second key. So either one, you can find it. If you use the one on the natural log, the ln, it gives you a space to enter the next part. So you're doing negative 50 divided by 50, or just negative 1. And this calculates to, I'm going to go ahead and make a round here, but I don't want you to round, I want you to keep it in your calculators, but it comes, this is my rounded answer, over 50. So I'll just keep it in the calculator and divide by 50, and so I come up with an average rate of change for the first part to be 2.94, and that would be milligrams per minute. Okay, I want you to go ahead and calculate this one on your own. So the second part of this problem, from 50 to 150 minutes. So this is the amount of pain reliever that's still in a patient's body after taking a pill 150 minutes later. So go ahead and try to calculate that on your own. You can pause the video if you need to. Alright, so then as we continue through this, it's interesting to look at the average rate of change, but it's going to be more important to be looking at the instantaneous rate of change. And that is the rate of change of a function at a certain time, so at an exact time. If given the function values before, during, and after the required time that you're looking for, the instantaneous rate of change can be estimated. So we're going to look at the maple syrup example again, but this time we're going to be looking for the rate of syrup poured out at exactly 4 minutes. So for that, we're going to find the average rate of change from 2 to 4, and then, or from 4 to 2, and then also from 4 to 6. So we're looking at those two different average rates of change. So we're going to have 54.03 minus 35.83 divided by 4 minus 2. And then we're going to find it again over here, 68.11 minus 54.03 divided by 6 minus 4. So we calculate those two. I'm going to give you a second. Go ahead and pause the video and calculate both of those. Come up with these as your rates of change. So we had 9.1, and these we were doing gallons per minute, and 7.04 gallons per minute, looking at from 6 to 4. Again, we know it's going down because there's less syrup left in our barrel. All right, let's go ahead and narrow in a little bit more on t equals 4, and so here we're looking at from 4 to 3.8 minutes, so a much smaller window of time we're looking at. So as you notice, we've done this narrowing in process before. So you're going to go ahead and calculate again. So you should have come up with 7.9 gallons per minute if we're coming from 3.8 to 4 seconds, and from and 7.7 gallons per minute from 4 to 4.2 seconds. We're going to repeat this process again. Go ahead and pause your video and take a second to try this for the next section. Okay, so what you've calculated here is that coming in from 3.98 seconds to 4 seconds, so almost 4 minutes, excuse me, I keep saying seconds, we're looking at 7.75 gallons per minute. And coming in from the other side, we've got from 4 to 4.02, from 4.02 minutes, you've got 7.85 gallons per minute. So these are approaching somewhere right in the middle there, and that would be the idea. So as we're getting closer, we're kind of narrowing in down to no time, and we're looking at exactly 4 minutes. So in a conclusion here, as the interval of time from A to B gets smaller and smaller, the average rate of change, our slope, gets closer to the instantaneous rate of change. So this is our we can use some symbolism for this, because we mathematicians like to use symbols rather than all these big words and long sentences. So we have the change in time, because this little symbol, this delta, is the change in time approaches 0. Okay, our average rate of change becomes our instantaneous rate of change.